Alrighty, looks like there's gonna be a hard today. I'll give it, let's say like an hour and a half to try to get this. Maximize spanning tree stability with upgrades. You're given an integer n representing n nodes numbered from 0 to n minus 1, and list of edges where edges I is u, v, s, and must. uv indicates the undirected edge between nodes u and v. S represents the strength of the edge. Must is an integer 0, 1. If must is 1, the edge must be included in the spanning tree. These edges cannot be upgraded. Spanning tree of a graph with n nodes is a subset of edges that connects all nodes together, i.e. the graph is connected without forming cycles and uses exactly n-1 edges. Right, okay. So there's like n nodes forming a spanning tree. Some of the edges must be connected. Okay. You're also given, and I guess there's 0 is optional. Okay. You're given integer k, the maximum number of upgrades you can perform. Each upgrade doubles the strength of an edge, and each eligible edge can be upgraded most once. Stability of a spanning tree is defined by the minimum strength score among all edges included within it. I mean, you're given a minimum number of upgrades you can perform. So the spanning tree has exactly n-1 edges. Some of them must be there. So you're choosing between the optional n-1 minus number of must edges. I wonder why they would even include the strength of an edge that is must, right? Because that's automatically part of the stability. Well, whatever. So there's 2 edges, 3 nodes. K is 1, so you have to upgrade at most 1. This is a must one, so you have to upgrade this one because this one's optional. And this one, so stability should be 3? No. Each upgrade doubles the strength of the edge. Return the maximum stability of any valid tree. It is not possible to connect all nodes to return negative. Edge 0, 2 has a strength of 2, must be included. Edge 1, 2 has a strength of 3, which must be upgraded to 6. The resulting spanning tree has 2 edges with strength 2 and 6. The minimum strength in the spanning tree is 2, which is the maximum possible state. What am I returning? Returning the minimum strength score among all edges included within it, which is the maximum possible stability. Stability of a spanning tree is defined. Return the maximum possible stability. Oh, okay. So you're trying to find the maximum minimum. Okay. The maximum minimum. So here, 3 edges, or 3 nodes, so you have to have 2 connected edges. K is 2. All 3 of these are initially optional, so you have to upgrade 2 of them. So you're trying to upgrade till you have the highest min possible. So there's a 4 connecting 0, 1, a 1 connecting 0, 2. So this is a triangle, 0, 1, 1, 2, 0, 2. So any 2 of these should work. So I guess you do 4 and 3. Upgrade this to be 6. Upgrade this to be 8. Stability. So it doubles, and then the minimum 6. Since all edges are optional, k equals 2. Upgrades are allowed. Upgrade edge there, 4 to 8. Upgrade there, 3 to 6. The minimum is going to be 6. And so that's the highest. If you included the other one, it would have been 2. It's pretty high acceptance rate for hard. This one's not possible. Okay. How to do this? Thinking this would be something like a binary search, maybe. So you maybe guess the highest stability and then search if it's possible. Binary search, 10 to the 5th nodes. It's doable, and log n for binary search time complexity. What to do, what to do, what to do? Probably should start with a graph, default dictionary, connecting the nodes to its neighbors, maybe a list of its neighbors. Default dictionary of a list, maybe. So let's say graph of node is equal to a list of, let's say, tuples of neighbor node and neighbor node and the string. I wonder, are there a possibility of duplicate edges? All edges are mandatory and form a cycle. It's possible that they already give you a cycle. Okay, there's no duplicate edges. Guess the first check is probably to make sure there's no cycles. I guess the first thing is probably build a graph here. So for every edge, which is u, v, s, and must in edges, graph of u appends the tuple that is v, s, and must. Maybe I should just do the optional edges here. Let's say I have a required edges here. And if it's, maybe I just have two graphs, like a required graph and an optional graph. So if it's must, then required graph at this u appends v and s. And required graph at v appends u and s. Else just the regular graph at u appends v and s. And the regular graph at v appends u and s. Okay. I'm just trying to make sure. I'm just trying to check if this thing forms a cycle. So how to do this? I guess it probably should be seen as how to do this, how to check for cycles. Scene should be a set. I guess I iterate over every node in n for node in range n. I'll do if the node is in scene, if the node is in scene, then skip. So how would I tell it's a cycle? So if I have 0, let's say this is all. So 0, I add, start 0, 0 connects to 2, 0 connects to 1. 0 connects to 2, 0 connects to 1. Node isn't seen. Continue. That's my guess what I should be doing. Then maybe I have a process stack. And while there is a process node, then current equals process pop. So processing node 0 means that I should do something like for every neighbor in the graph, in the required graph of the current node. This should be the first time I see the neighbor, otherwise it's a cycle, right? If the neighbor is in scene, return -1. Otherwise process should append neighbor. Actually, this should have neighbor in the string, which I don't care about. This is a tuple. Process appends the neighbor. I think I should be saying that the neighbor is now seen. Scene.addNeighbor. Probably should say here scene.addNode. So if I do 0 to my starting node, it hasn't been seen. Add 0 to the node, 0 to the scene set, adds 0 to the stack to process. While that stack occurs, while that stack is this, take node 0 out for every required neighbor in the graph next to 0, the neighbor in the string. The neighbor's already been seen. It's a cycle. Otherwise, take 1 out, add 1 to the stack to process. Scene is now including 1. Then it does 2. And then when it processes 1, then it should see that it's done this before. Okay. I think this should work for example 3. Okay, so this is just to check for bad starting tree cycle. Alright, so now it's the question of how to do the non-trivial case. I wonder if I should worry about. I wonder if I should like try to prune the edges. Is there some edges that could form a cycle with some optional edges that could form a cycle along with the required edges? So maybe I should try to remove those. Would that help? Yeah, it might help. Oh. Remove optional edges that would form a cycle. Seems like it might just do a lot of work for kind of a lot of work for not solving it, because that even if I remove the optional edges, it just might be that I don't really, it doesn't really get me much in terms of worst case scenario. It's still very unoptimized. Still maybe doesn't prune anything, like this case here, or like this case here. Pretty much all optional edges, so there's nothing to prune. Yeah, I don't know. This thing seems unlikely to help. Three nodes, 2 edges, 0 must. If I were to there's n nodes. In theory, there could be much more than n edges, or the size of the number of edges, size of the length of the edges could be much more than n. It could be like n squared over 2 or so. But it's not. It's kind of linear. In theory you could make any edges to nodes that only have one edge required, right? I wonder if that'd help. For every edge, for every node, if there's only one edge, move it to the required. I guess that's probably pretty easy to do. But I have to do that before checking for the cycle. Guess if there, this is going to affect cycles, right? If there's a cycle when it wouldn't be caused by a node that only has one edge. So maybe I can do something like and that would become a required edge, wouldn't it? That would become a required edge. But it would be the value of that edge is going to be twice as much. Minus one edge. Okay, so let's do like for every node in range n. If the node is not in required graph, and there's only one node, there's only one I wonder if it's possible to just not have all. I wonder if it's possible to just not have a particular edge to a node. Like it's just totally isolated, so no edges. Guess there's nothing here that indicates that it has to have an edge. In which case that's another faulty tree. So if the node is not in the graph and either the node is not in the required graph and the node is not in graph or okay, maybe this is compound. If node not in graph at all, no connections node, no edges to node. Else if the length of the graph, the optional graph to this node is equal to 1, only one edge, make it required. So what I'd do would be I'd say the neighbor and the strength is equal to graph node at 0. Or I can just do graph node pop. And then I would say required graph of this node is now appends this neighbor and twice the string. So normally for required edges, it's the original value of the string. And since we're transferring it from optional to required, it has to be doubled. And then I would have to change the neighbor graph. How would I change the neighbor graph? I have to remove this from the neighbor. To remove it from the neighbor, it makes sense to have it in a list. It have to be a set of tuples. How awkward. I mean, I guess I can do that. A set rather than a list. Oh, sure. We'll go with it until it breaks. Okay, so the graph is now using a set within a list. Let's find still with a node in required graph. The node is not in graph. Don't think I can. Well, that's poor parenthesization. Length of graph of node equals 1. I think I could do pop on a set. Yeah. And then I would have to do graph of the neighbor, remove or discard this node in a string. And then I have to do something like required graph of the neighbor appends this node in string times 2. I guess. So pop. Yeah. Remove or discard. Keep on forgetting. Discard does not raise an error if it's not found. Remove does raise an error if it's not found. Okay. It's fine. Guess this should actually do example 1. It should force this to be required. K actually decreases, right? K is the number of times I need to change from optional to required. Go ahead and print graph. Is this going to actually print anything correctly? I'm not sure what this is going to print out. Just the memory location. Returns -1. Uh-oh. Uh-oh, spaghettios. Every node at the node. Alright, let's go at this part here. Shouldn't be returning a -1 here. Why is it returning -1? Ooh. So the first one it found a cycle. 0 to 1, 1 to 2. Find a cycle for this one. 0, scene add 0, process. Yeah, okay. So it went 0 to 1, and then it went 1 to 0. Right. Unfortunate. 0 to 1. 1 to 0. 0 to 1. 'It's going backwards, huh? So it just can't go backwards to its past. So maybe I should have a process start to destination. So previous and current. So for every neighbor in the current, the neighbor if the neighbor isn't the previous. If the neighbor equals the previous, then continue. Because that doesn't count as a cycle. Otherwise, if the neighbor isn't seen, return -1. I think that's right. And then the process appends the current and the neighbor. Okay, so no longer detected cycles from just going like 0 to 1 back to 1 to 0. And it does detect the last one to be a cycle. Okay. So it's printing out here. What is it printing out here? Required graph in the regular graph. Required graph in the regular graph. Technically, everything should be required. For example, 1 after detecting that there's only 2 possible edges, I think. Zero goes to 1, 2. 1 goes to 0, 2. 2 goes to 0 goes to 1, 2. No, 0 goes to 1. 1 goes to 0. 2 doesn't go anywhere. What I was thinking would come up. For every node not in the required graph. If the node is not in the required graph. So 0, 1 is all required. So the only node that is only 2 would work here. But we should be skipping node 0 and 1. Skipping 0, 1, and 2. Why is it skipping? I see. No, actually I don't see it. Why is it skipping 2? Because 2 should not be in the required graph. Yeah, so okay, I see. 2 is in the default dictionary, so this is a default dictionary. In here it's gonna be if length of required graph node equals 0. There we go. Okay, so it's skipping 0 and 1 because those have required edges, but it does move 2. Yeah, so 2 has to have required edge to 1. And now, yeah, okay. And now the set of things that are not required for 1 and 2 is empty. Okay, I think that's what I wanted. And this thing should have made it 6 as the edge, as the strength of the edge between 2 and 1. Okay. This thing shouldn't have done anything on example 2, I don't think. Yeah, example 2, pre and post is the same. We couldn't detect anything to be required there, which is correct. It's three edges, 2 required. Doesn't know which one is. Which one's to pick. Okay. What to do from there? If I were to edges to make. I'm trying to make the ones that are the highest strength. Optional edges to be part of the spanning tree. Trying to make the ones with the highest. I'm gonna do binary switch. If I would guess a random number, can I make every edge with that number or bigger? Which upgrade doubles the strength of the edge? Which would be hard. Because even if I just guess the maximum possible stability, it's still gonna, it's not like I can just go to every edge where stability is that or more and turn it on. It could just be that, say the maximum possible stability is 100. There's some edges that are 100 or bigger that I can turn on, but then there might be others that are bigger than 100 that I need to keep off. the nodes are 0, 1, 2, 3, 4. The nodes are just 0, 3. So this is like 50 between these nodes. So 55 here between 0 and 2. 45 here between 2 and 3. And 40. So in theory I'd want like 50, 55, 45 to connect it. But how would I tell? You'd start by maybe starting on the highest. Greedy approach. Then the greedy approach always works. Probably not. Greedy approach could make a cycle. Like if there was a connection between between 0, 1, 1, 3, 2, 2, 3. Just form a circle.